Thanks for the introduction. So this work was done in collaboration with Max Stengel and one of his former students, Andreas Jafino from Barcelona, and then David Vanderbilt from Rutgers. So in the last several talks, we've heard a lot about ferroelectricity. I'll be talking about something a little bit different. I'll be talking about flexoelectricity. So let me just remind everyone what flexoelectricity is. So flexoelectricity is polarization that's induced by a strain gradient that might be present in a material. For example, if you bend a cantilever of a certain material, then you would generate a strain gradient through this cantilever. So the reason that we're interested in flexoelectricity in general is, first of all, the possibility that you could make novel types of devices using the functionality of polarization induced by a gradient, and also the fact that in nanoscale devices, oftentimes large strain gradients are present unintentionally, and so since flexoelectricity is universal to all insulators, it could play a role in the properties of such devices. So the way that we talk about flexoelectricity is very similar to the way that we talk about piezoelectricity, for example, through these flexoelectric coefficients, which relate the polarization to the strain gradient. And so the strain gradient is just the derivative of the strain with respect to position. And there can be a variety of different types of strain gradients, longitudinal, shear, or this kind of bending or transverse type gradient. And so those make up all of the elements of the flexoelectric tensor and describe the response. So in this talk, what I'll be talking about is flexoelectricity in a certain material, specifically boron nitride, which I'll briefly introduce. Then I'll also very briefly summarize our methodology for calculating the flexoelectric response from first principles using density functional theory, and then finally talk about how we understand the different contributions of flexoelectricity in this material, boron nitride. So we've heard a lot about 2D materials so far in this session. Boron nitride is kind of an especially simple 2D material. So it's made up of these 2D planes of boron and nitrogen that are van der Waals bonded together. It looks very much like graphene, except for instead of having two carbon atoms, we have a boron and a nitrogen. And since we've broken the sublattice symmetry of the graphene structure, we get an insulator, and with actually quite a large band gap of around 5 eV. So the reason that we're interested in flexoelectricity in boron nitride is that in general in 2D materials, strain engineering is a very interesting area. So oftentimes we think of being able to just stack 2D materials together regardless of their lattice constants, but unintentionally strain is often present when these sort of heterostructures are made. Strain can also be used intentionally to modify the properties of the electronic structure of 2D materials in interesting ways. And one thing that I'll just highlight is also what has been found very recently by some colleagues of mine is that if you take 2D layers and you twist them with respect to each other, then as you probably know, you can generate interesting moire patterns, and the domain walls between the moire patterns actually become electromechanically active. So these are PFM images for twisted boron nitride. The same thing actually works for twisted bilayer graphene, which if you're interested, we can discuss after. So anyway, the idea, or the main question is whether the 2D-ness of these types of materials, in our case boron nitride, affects the flexoelectric properties. So these are just some schematics of some of the flexoelectric components, or the components of the flexoelectric tensor, where the red lines are these tightly bound 2D boron nitride layers that are van der Waals bonded to each other. And so we can see for a lot of these different components, these layers are shifted or displaced with respect to each other. We might expect the 2D-ness of this crystal structure to play a role. Okay, so that's just a quick introduction to boron nitride. As I said before, I'll give a very quick introduction or quick overview of our computational approach. So this has been the culmination of many works throughout the years. And if you've seen talks from us in the past, this has really been the main focus. But I will just kind of give a flavor of how we calculate the flexoelectric response from first principles. So the first thing that we do is we realize that we can identify different types of strain gradients in different types of acoustic phonons. And this is a computationally very attractive way of thinking about strain gradients because it restores periodicity. And if we want to do a bulk calculation, periodicity is always our friend. So when we have these atomic displacements that create a gradient or create a phonon, these will be accompanied by a polarization. And to linear response, this polarization will be modulated by the same phase as the acoustic phonon that we're modeling. And so because a gradient can be considered as a very long wavelength acoustic phonon, we do an expansion in a long wavelength expansion or small wave vector expansion and calculate the polarization response at these different orders in Q. And so what I'll show is that these different coefficients of this expansion enter into the different components of the flexoelectric response of this material. So just for those who are interested, I'll just flash up the computational details. These are density functional theory calculations that I'll show using LDA, norm conserving pseudopotentials in the Abinit code. And the specific implementations that I'll use to calculate the response are given in these two papers. All right, so let's talk specifically about boron nitride and the contributions to flexoelectricity in this material. So in general, for the bulk flexoelectric response of a material, we have three contributions, which I'll go through one by one. The first is that I'll mention is a clamped ion contribution, what we call lattice mediated, and then what we usually refer to as a mixed contribution. So the clamped ion contribution is the contribution of the valence electrons to the flexoelectric response. So one way to think about it is if we start with a very symmetric elemental crystal and we apply a strain gradient, for example, by varying the x strain in the x direction, then the symmetric environment that each atom sees is broken. This is reflected in the electronic structure around each ion, and a polarization is induced. And so it turns out that this clamped ion contribution is exactly given by this second order expansion coefficient in the long wavelength polarization expansion that I showed a few slides ago. So this is the case for the purely longitudinal component, but in general we can calculate all of the different components by taking second derivatives of this polarization response with respect to phonon wave vector. So here I display some results of the clamped ion coefficient in units of nanocoulombs per meter. These red cases are the ones where you might expect the 2D-ness of boron nitride to play a role. We also have two components that are just purely in the plane of the boron nitride. So these numbers probably don't make too much sense on the surface, but one thing that we can see is that we see a similar behavior in the clamped ion contribution as we see in a lot of the 3D materials that we calculate. Namely that the longitudinal and transverse type components are approximately equal to each other. The shear components are a lot smaller. So I'll just mention also that the magnitude of these components is similar to what we see in 3D materials like perovskite oxides. So far there's no big surprises. One thing that we can also see is that some of these coefficients can be understood by a so-called rigid layer model, which just means that we consider these 2D layers to be rigid charge densities that are concentrated or diluted with respect to each other. And if we construct a model based on that and we compare it to our actual calculations, they agree quite well for C lattice parameters around the experimental one. So I won't go into any more detail about that. Just to move on to the second contribution that I have here, which is so-called lattice mediated contribution. And the way to understand this contribution is by considering a crystal that is ionic. So if a crystal has some ionic character, then it will have different Boron effective. It will have atoms with different Boron effective charges. The Boron effective charge defined as the change in polarization when you take an atomic sublattice and you move it. And so when we apply a strain gradient, these ions with their different Boron effective charges will rearrange with respect to each other, and this can also give a polarization response. So as I said, so boron nitride is such a crystal. It has an ionic component, and so it has non-zero elements of the Boron effective charge tensor. They're different in versus out of the 2D plane. And in order to obtain the lattice mediated contribution, we multiply these by elements of what we call an internal relaxation, flexoelectric internal relaxation tensor, which is just which just describes how, when we apply a gradient, these atoms rearrange inside of the crystal. And these Boron effective charges are exactly the 0th order term in our polarization expansion. So I've added to this table now the lattice mediated contributions. The lattice mediated contributions are a little bit difficult to parse physically, because what we found is that there are larger internal relaxations when we consider out of plane components. So that's this L tensor. But the Boron effective charge out of plane is smaller than the Boron effective charge in plane. So there's somewhat of an error cancellation, and so the numbers are a little bit difficult to interpret. What I will say is that compared to materials like perovskite oxides, these numbers are orders of magnitude smaller than what we usually see, or 1 or 2 orders of magnitude smaller. So finally, the last component to the flexoelectric, or the last contribution to the flexoelectric response, is the so-called mixed contribution. So at least I find that this contribution is the hardest to think about physically, so we'll just think about it in the very specific case of boron nitride. So one of the interesting things about boron nitride is that if we consider a single layer of boron nitride, it's actually piezoelectric. So if you apply a strain in the y direction, then you get a polarization in the y direction. So bulk boron nitride is not piezoelectric, exactly because the polarization that you get when you apply a strain, now this is the y direction. So the polarization in one layer cancels the polarization in the other layer. And so in the case where you have a strain gradient, then these layers may not be different, and these local piezoelectric responses can contribute to an overall polarization. So in order to calculate the mixed part, we need this sublattice or atomically resolved piezoelectric contribution, which turns out to be exactly the first order term in our polarization expansion. And then we need a similar tensor as I introduced for the lattice mediated contribution, which describes the internal relaxations within unit cells when a uniform strain is applied, and that kind of activates this localized piezoelectric response. So again, we can add a row for the mixed contribution. Because these piezoelectric responses are only in the XY plane, then the only contributions are for these kind of purely in-plane flexoelectric coefficients. Boron nitride actually has a fairly sizable piezoelectric response, depending on how you look at the dimensionality. But the mixed component of the flexoelectric response is pretty modest, on the order of all of these other responses. And the reason is that because these are all in plane, boron nitride is pretty stiff in plane, and again, those internal relaxations are small. So putting everything together, we see that all of these contributions are of similar order in boron nitride and need to be all included to get a full quantitative picture of the flexoelectric response. In the end, we also get this relation that the longitudinal and the transverse components are similar, or the same order, and we see the shear components are actually very small as they involve shear between these 2D layers. So in conclusion, boron nitride and other 2D materials are very interesting for strain engineering. And I tried to briefly describe how we have the full first principles toolkit to calculate the bulk flexoelectric response of boron nitride and include all of the different components to get a quantitative picture of the response. So thank you.
Thank you. That was very nice. You didn't say anything. I think your abstract said that you weren't going to discuss the surface effects. In this context where you're looking at a single layer of boron nitride, should I think of any such surface effects as coming from the edges?
So, this is for what I would say is bulk boron nitride.
Oh.
So, yeah. So the surface effects I think will be quite interesting in 2D materials because the surface is somewhat trivial compared to a 3D material. But we're still working on some aspects of that. Does that answer your question? So this should be thought of as properties of a bulk boron nitride.
But if you were to do, maybe you don't want to address that, but if you were to do a single monolayer, how should I think about the surface effects in that case?
So I think I'm dancing around your question, but a single monolayer would be conceptually very difficult because it's piezoelectric. And if a material is piezoelectric, then the calculation of the flexoelectric coefficient is not so well defined. Right? If the lower moments are non-zero, then the higher moments have some issues. You could imagine if you're asking, for example, about the surface of a infinite bulk piece of boron nitride or an even number of layers of boron nitride, which is non-piezoelectric. So my instinct would be that the surface effects would be quite small because like I said, a lot of these coefficients you can kind of think of as rigid charge densities moving with respect to each other. But there are some questions about electrostatic boundary conditions and things like that we're still trying to work out.
Any other question?
In principle, are there linear response or higher order response methods for calculating these coefficients?
So I didn't like I said, I didn't touch on too much on the actual physical implementation, but now in some of these later later citations, later papers that I just flashed up here, the calculation is fully linear response. So just like calculating the phonon responses or electric field responses, so on.
Okay, so now we have to move on. So let's thank our speaker again.